Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2021 physics exam for the Northern Hemisphere, short answer questions, and we're doing questions 1 to 9. And so yeah, like always guys, before I start this video, if you guys want, private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. So 3 marks, a small sphere carrying a charge of negative 2.7 microcoulombs is placed between charged parallel plates as shown in figure 1. Alright, so the potential difference between the plates is said to be 15.5 volts, which just holds the sphere stationary. Alright, the electrical field between the plates is uniform. In which direction, up or down or right or left, will the sphere move if the voltage is increased? Alright, so let's have a look at this. I know for a fact that this is a variable, battery. You can change. So this here is the positive. So I know this here is the positive plate, just because this is the largest, and this here is the smallest, so it has to be the negative plate. So, and of course, this is your ground. And so, because it's a negative charge, it's going to be actually attracted up. It's going to be attracted up. So you might realize, you'll be like, wait. First, it was stationary. What does it mean when it's stationary? When it's stationary because the force of gravity your force of gravity and, of course, your electrical force, so F electrical, are both equal in magnitude. So what's happening is they are cancelling each other out, and that's why in the small sphere is actually levitating and it's stationary at that point. It's just because, the force of gravity is equal to the electrical force. Pretty much that's why. So it says in which, direction, up or down or right or left, will the sphere move if the voltage is increased? Okay, let's think about this. We know that your electrical force, remember your force of gravity is only, related to mass times gravity, which is nothing got to do with voltage. But your electrical force is known as Q times electrical field. And your electrical field is your voltage over distance. So if you increase your voltage, you're increasing your electrical field strength. So if you increase this electrical field strength, we're increasing the electrical force. So imagine now, in this case, this electrical force is larger than, so this electrical force is now larger. So your force of electrical. So overall, this is now an unbalanced force, and there's a net force upwards. So the actual, sphere is going to go up, pretty much. Done. Calculate the value of the electrical force that is holding the sphere stationary if the plates are 2.0 millimeters apart, and show your working out. So we want the electrical force. So we know that the electrical force, so force electrical, let me write that, is just Q times electrical field strength. And so your electrical field strength is what? It's, again, we said voltage over distance. And we know the voltage was 15.5 divided by the distance, which is just 2.0 times 10 to the negative 3 to make it to meters. Because it's a millimeter. So that's going to give me what? So 15.5, 2.0 times 10 to the negative 3. That gives me an electrical field strength of 7750 volts per meter. And so now we have our electrical field strength. All we have to do is multiply them. So force electrical is just your charge. It is, we're given the charge. It's 2.7 micro, which is times 10 to the negative 6. And your electrical field strength, which was 7750. So let's multiply these two together, and we should get our force. And so that gives me two significant figures, 2.1 times 10 to the power of 1 to negative 2. I just want to double check that for my calculator. So 1, 2. Yep, that looks good. Beautiful. Question 2. An electron is accelerated from rest by a potential difference of V0. It emerges at a speed of 2.0 times 10 to the power 6 into a magnetic field B of strength this, and follows a circular arc as shown. Kind of a typical question. It looks like an electron gun question. And so calculate the value of the accelerating voltage, show your working out. So because we're given the speed, you should straight away realize that you should use your electron gun formula. So your electron gun formula is pretty much half mv squared over equals qv, where v is our accelerating voltage, and that's what we need to calculate. So to get voltage, pretty much, divide both sides by Q, pretty much. So it'll be mv squared over 2Q. Yep, that looks good. And so what is our mass of our electron? The mass of electrons in your formula sheet, it's pretty much 9.1 times 10 to the power of -31. And so your velocity was what? It was 2.0 times 10 to the power of 7. Yep, squared. All being divided by 2 times your charge of an electron, which is also in your formula sheet, which is just 1.6 times 10 to the power of -19. So putting this all in my calculator, I should get the voltage. And so I get, we went in kilovolts, so I'm just going to divide it by 1,000. I get to two significant figures, 1.1 kilovolts. So B, explain why the path of the electron in the magnetic field follows the circular arc. This, I promise you, this question here is just similar to the 2019 exam question. They always ask this question for some reason whenever you do this question. So it's very, very easy to get full marks. Just need to put this kind of answer in your formula sheet because it's in your summary sheet. And so, yeah, this is why it actually follows a circular path. It's because there is a magnetic field that's going to be produced because of if you use your right-hand slap rule. There's a magnetic force that's going to be produced, which is perpendicular to its velocity. So there's going to be a force that's going to be produced. And so this force is in constant magnitude. It has a constant magnitude. And so, but you remember it changes, the direction always changes. So if now the force is pushing a little bit upwards, so the ball, the electron will go here. But remember, the force will be now here, and the velocity is going to go here. So it just curves in a nice uniform sphere. If the whole thing was in a magnetic field, it would just beautifully cover a nice sphere. It's just because, like always, there's a force that's being produced, the magnetic force, which is perpendicular to the velocity and is constant in magnitude. That's all you need to really, really pretty much talk about to get full marks. Because I've seen this question in the 2019. So it's very, very, if you make your life easier, just write it in your summary sheet or formula sheet. So what we're going to say is magnetic force acts perpendicular to both velocity and magnetic field. This force is always present and is constant magnitude. As a result, the particle's motion curves into a circular arc. That's it. If the whole thing was, had magnetic fields like out the page, the actual thing will go like a nice uniform circle, and it will just keep going like that. If the whole thing was in a magnetic field, but luckily it will curve and it will go out at the same velocity as it came in. Beautiful. Calculate the radius of the path traveled by the electron. Show you working out. What a beautiful, easy question. So you should know that radius is just calculated as mv over qb. So just put all our information there. It's one of the most nicest questions to really get. So your mass, of course, of the electron was 9.1 times 10 to the negative 31. And your velocity was stated here, 2.0 times 2 times 10 to the power of 7. The charge of the electron is 1.6 times 10 to the negative 19. And the magnetic field strength, which was 2.5 times 10 to the power negative 3. Putting this in my calculator, I should get the radius. And so I got to two significant figures, 4.6 times 10 to the power of negative what? So 1 and 2. So negative 2 meters. 1, 2. Yep, that looks good. Question 3. The motion of the Earth's moon can be modeled as a circular orbit around the Earth as shown in figure 3. Alright, so the mass of the Earth, we're given the mass of the moon, radius of the moon, orbit around the Earth, okay, and the universal gravitational constant. Calculate the magnitude of the gravitational force that the Earth exerts on the orbiting moon. Give your answer correct to 3 decimal places. You don't really need to worry about calculating that because whatever they tell you, so there's, of course, you know, there's going to be two forces that are going to be produced in this. So the force is going to be attracted to the Earth, which creates a force. And also, the Earth is going to be also having the same force, the same magnitude of force, but in the opposite direction, because they're being attracted to each other. So, it says just calculate the magnitude of the gravitational force that the Earth exerts on. So the Earth exerts on the orbiting moon. Beautiful. So you don't have to worry because both. You don't need to know which direction or anything. It's just both forces will give you the same. The force is the same for both. So just using your formula, force of gravity is equal to G m1 m2 r squared. G is 6.67 times 10 to the negative 11. M1 is the like mass of the Earth in this case. Let's pull that. Your second mass, which is the mass of the moon. Yep. All being divided by the radius, orbital radius squared. Which in this case is 3.84 times 10 to the power of 8 squared. That looks good. 3.84 times 10 to the power of 8 squared. So I get to how many significant figures? 3 significant figures. 1.99 times 10 to the power of 20 newtons. What a large force. Beautiful. Question B. The average orbital period of the Earth's moon is this. The moon is moving slightly further away from the Earth at an average rate of 4 centimeters per year. Given this information, will the average orbital period of the Earth's moon decrease, stay the same, or increase? Explain your answer. Alright, so what's happening is the radius is increasing over time. And so I would suggest by looking at Kepler's law here. So we know the period is square root of 4 pi squared r to the power 3 over gm. And so we can see that your period is proportional to the square root of r to the power 3. So because our radius is increasing, it's increasing 4 centimeters per year, so it's actually increasing slightly, your period will also increase. So pretty much that's it. And so the way you would get those 3 marks is first stating that it increases, your period will increase, and pretty much explain it by using this law, which is Kepler's law, and write it down and state this proportionality, that t is proportional to the square root of r to the power 3. And so hence the orbital radius increases, the period also increases. That should just give you those 3 marks. A nice easy 3 mark question there. So the period increases. And so as from Kepler's law, Kepler's third law, I think it is. Yeah, t is equal to the square root of 4 pi squared r to the power 3 over gm, where t is pretty much proportional to the square root of r to the power 3. So we've written that. And so, hence, as the orbital radius increases, the period will also increase. Done. Next question. Question 4. Let's have a look at this question. Just use a different color. Figure 4 shows a schematic diagram of a simple one-coil DC motor. A current is flowing through this coil. Alright. Draw an arrow on figure 4 to indicate the direction of the force acting on the side JK on the coil. Okay, let's find out what the direction of the current. So we can see this is your this is your positive terminal. So the current's going to go this way, that way. It's going to move. So in terms of JK, the current's going pretty much this way, and so of course the magnetic fields are going to the right. So using your right hand slap rule, your thumb is going to go to the direction of the current, and your fingers are going to go to the direction of the magnetic fields lines, and so your hand, your palm should be acting downwards. So there's going to be a force downwards going to be produced here. Let me rub these out. So only at this point, there's going to be a force that's going to be downwards on the JK. That's it. Explain the purpose of a split ring commutator. What a beautiful question. If you guys don't have the definition of a split ring commutator or a slip ring commutator or a slip rings, you need to have them in your summary sheet. They are so much, like, they kind of repeat in every exam, and they are very easy to get full marks for. Make sure to always have the definition in your your summary sheet. So I'm going to have a look at my summary sheet right now, because I do have a nice definition that get for these 2 marks. And yeah, all we have to just, again, say the split ring commutator reverses the direction of the current every half turn in order to keep the coil rotating in the same direction continuously to get those 2 marks. Nice and very precise definition. So make sure you have this in your summary sheet. It's very easy. So the split ring commutator reverses the direction of the current every half turn in order to keep the coil rotating in the same direction continuously. Beautiful. Nice, precise 2 marks there. Next question, question 5. Physics students who are investigating the generation of electricity spin a coil at a constant, 10 rotations per second. So that's your frequency, yeah? It's a rotations per second, so that's your frequency. In a uniform magnetic field, they observe that the output of an oscilloscope is that the experimental setup is shown in figure 5. The peak voltage produced is 5 millivolts. So the students are investigating the generation of electricity by spinning a coil. So if they're spinning a coil, this is actually a DC generator. How do I know? It's a generator because we're spinning it, and also it's DC because it has a split ring commutator. So you should be careful, yeah? Don't forget, this here is going to produce a DC output voltage. Normally it's supposed to have a slip rings, but yeah, they've used here a split ring commutator. On the axis below, sketch the voltage versus time graph observed on the screen of the oscilloscope for one complete rotation of the coil from the position shown in figure 5. Include appropriate scales on each axis. And so how many marks that is? Don't know. 3 marks. Wow. Easy. Let's do that. So what I'm going to first do is I'm going to draw basically the magnetic flux over time graph for one rotation. Which is what? In this case, because, we start, the magnetic field lines are going to start, the flux is going to be 0 because they're not passing into the plane of the loop. So it's going to start at 0, and so as it rotates, it's going to increase. So it's going to look like this. One full rotation will look like this. How do we know the time for one full rotation? That's the period. And to calculate that period, remember your period is just 1 over your frequency, which is 1 over 10. Which is 1 over 10, which is 0.1. So it takes this here, it's 0.1. And so that's not very important right now. Just now we've got the magnetic flux diagram. We can use this to easily calculate, to visualize our EMF graph. So our EMF graph, wherever there's a turning point, it's going to be on the t-axis. So for example, if there's a turning point here, so it's going to be in the t-axis. And so you can see how from here, it's a positive gradient, but just think of the opposite. If it's a positive gradient, it has to be negative. So it'll be below. So it'll look like something like this. Like that, like this, and like that. And so overall, that's one full rotation in terms of EMF. Why is the gradient positive, but why do we make it negative? Because remember, your EMF is just negative N change in theta over change in flux over change in time. This change in flux is pretty much the gradient of that, which is positive, but remember there's also a negative, so you have to multiply it by negative to make it that graph, and that's it. So that's how a full rotation would look like. So let's do that. So I'm just going to say this, I'm going to draw another kind of, so here, points here, my point looks here, and that points here. So now we're just drawing it nicely. Like that. So we've drawn a rotation, but that's only if it had slip rings. Remember, we're using a split ring commutator, so it's going to rectify the negative voltages. So you need to be careful. So you need to make sure these negative parts, are going to be rectified like that. So it's going to look like that. And so this here too is going to look like that. So we can rub these parts out pretty much. Look at that. So that's actually, yeah, one full rotation. And so this here, because we only one rotation, we know the period was 0, so 0.1, that's one full rotation. So halfway is going to be pretty much 0.05 seconds. Yeah. And of course, it says include appropriate scale. So this here has to be the, in terms of millivolts, and we know that we were producing what? 5 millivolts. So this will be 5 millivolts, and yeah, that's it. Beautiful. Next question, question 6. Let's have a look at this question. So Gera and Kao are investigating the electromagnetic induction. They have a single wire loop of dimensions xy long and yz wide, which is placed in a uniform magnetic field of strength this. The loop is rotated clockwise about the axis as shown in figure 6. All right. And we're using a slip rings. Good. Explain the purpose of a slip ring. Slip rings in the apparatus shown, in figure 6. You should also have this definition in your summary sheet. And here it is. From reading my summary sheet, I know that it's pretty much a component that's used to maintain a constant electrical connection between a stationary external circuit and a rotating coil. It is so important to have both a split ring commutator and a slip ring definitions in your summary sheet. They come up in exams most of the time. And yeah, let's write that down now. I can't believe that this exam had both the definition of split ring commutators and slip rings together, which is quite easy to get. So let's write that down here. It's pretty much a component used to maintain a constant electrical connection between a stationary external circuit and a rotating coil, That looks perfect. Yep, a component used to maintain a constant electrical connection between a stationary external circuit and a rotating coil. Nice. If you don't have it, make sure you write this definition in your summary sheet. Calculate the size of the magnetic flux for the loop when it's orientated as shown in figure 6. Show you're working out. So as it's oriented here, we're going to have a maximum magnetic flux cause the field lines are going to pass through the plane. And so let's calculate that flux. Easy. So your flux is just your area times your magnetic field. So area is the dimensions here, so 0.03. So 0.30 times your 0.020. That's you're going to give us our area, and we just need to find the magnetic field strength, which is 0.2. And that looks good. So writing down our calculator. That gives me to two significant figures 1.2 times 10 to the power of 1, 2, 3, 4 times 10 to the negative 4. Just want to double check everything's written nicely. And it looks good. Yep. 1.2. So 1, 2, 3, 4. Negative 4. Beautiful. The loop is rotated by Co at a constant frequency, and an EMF is generated in figure 7 to show the generated EMF versus time trace observed on the screen of an oscilloscope. Alright, calculate the frequency of rotation from the oscilloscope trace shown in figure 7. Beautiful. So if we want the frequency, remember frequency is 1 over t, so your period. We need our period. Remember the period is how long does it take for one full cycle. So one full cycle, as we can see from this graph, is it takes 0.2 seconds. So it's just going to be 1 over 0.2 seconds, which is 1 over 0.2, which is 5 hertz. Done. D. Go now doubles the number of turns in a loop from 1 turn to 2 turns, creating 2 loops. The loops are again rotated at the same frequency. On figure 8 below, sketch a graph that shows the resulting variations of the EMF versus between point A and B as labeled in figure 6. The original output is shown in dashed lines. Beautiful. So we know that what happens to our EMF if you double the number of loops. We know that if you double your number of loops, what's going to happen? Your N, if you double your value of N, so you get, your loops, which is 2N, your amplitude or your EMF is going to double. But luckily, it doesn't. Your period's not going to get affected because luckily we're given that the constant, it's at the same constant frequency, so your period doesn't change. So the only thing that changes is your amplitude. So the period's going to be the same. So just doubling the amplitude, so you're doubling your voltage. So in this case, all these points are going to be the same because. Yep, all these points are going to be the same. The period's the same. And just so you know how it's 4 volts per meter, it will just double. So your amplitude will be 8 millers per volt. So there, right over there, and this one right over here. And beautiful. So now it's just going to look like, why is it? I hope that kind of fixes it up. Can I do that? Oh. That looks nice. Oh, it kind of looks very bad, but something like that. And all I'm just going to do is, not duplicate, but take this over here. So I'm going to take this, and I'm just going to duplicate it and put it right over here too. So it'll be the same here. And so I want to duplicate this, but a little bit rotate it this way. To make sure it fits perfectly on this one too. Like that. Also duplicate that one, and it's going to also rotate it nicely here. And pretty much that's it. That looks perfect. So it will look like this. You can only see that the amplitude has doubled, but the period and everything is pretty much the same. Perfect. Question 7. Let's have a look at this. Angela and Janik are installing 2 low voltage lights in their outdoor garden. They have 240 volts RMS AC transformer with an output voltage of 12 volts RMS AC. Each light has a constant resistance of 6 ohms. For the purposes of this calculation, assume that the transformer is ideal. Alright? Describe what is meant by an ideal transformer in terms of input power and the output power. If you don't know what an actual ideal means in terms of transformers, it just means that there's no power loss in the transformer. Overall, what it just means is that the input voltage, so your input power is going to be equal, so your input power is going to be just equal to your output power. So there's actually no, power loss in that transformer. So ideal means no power loss in transformer. Done. What a nice, easy mark. B. Calculate the ratio of the number of turns of primary coil to the number of turns of the secondary coil. So we want NP to NS. So that's just equal to your VP dot VS. So the number of primary is just equal to the number of secondary coils is just equal to the voltage primary to the ratio of the secondary voltage. So which is, what's your voltage primary? It's 240 volts RMS to 12, which is pretty much 20 to 1. There's a 21 to ratio, so 20 to 1 ratio, done. C. Each light is designed to operate at 12 volts RMS. Calculate the power dissipated in one light when it's operated at 12 volts RMS. Show you're working out. So we want the power. So we're given the voltage, and we're also given the resistance, so we know that power is just voltage V squared over R, one of our formulas. So our voltage is 12 squared over your resistance, which was 6, was it? Yep, 6 ohms. So let's do that. 12 squared over 6. That gives me 24 watts. Done. Angela and Janique now connect the first light 1, to the transformer using the 2 wires, each 12 meters long, as shown in figure 9. Each wire has a resistance of 0.05 per meter, alright? So we're given that, so we have a transformer, and so we're given 12 meters of wire from here to here, but of course we double it because we also have the same length of wire here. So overall we have 24 meters of wire. And from this question, it tells us that every meter, that has the wire has a resistance of 0.05 per meter resistance. So I'm just going to pretty much multiply that by that 0.05 to know the resistance in the transmission line, the overall resistance. 5 times 0.05, it's 1.2 ohms in those transmission lines. All right. Calculate the RMS voltage across light 1, show you working out. What I'm going to do is I'm going to just simplify this whole circuit into a nice circuit, like a nice, very easy to understand circuit. So we have this voltage output that's coming, and so we're going to have, all right, we're going to have our transformer, this transformer, and so we will have also our transmission lines, and we're going to also have our globe. Oops. This nicely, and so this is going to be 240 volts, we said, and this here is going to output 212 volts, and we know also this is 1.2 ohms, and also each light has 6 ohms. And so if we want to calculate the RMS voltage across the light 1, what we're going to probably do is we can easily calculate the current that's running through the secondary, this circuit here, because we know overall this is a series circuit, so we can actually add to get the overall resistance. So overall resistance, it's just adding the resistance because it's in a series circuit. So 6 plus 1.2, which is 7.2 ohms. And so we got that. And so now we already also have the overall voltage in that circuit. We know about Ohm's law to calculate the current. It's just voltage over resistance is your current. So your current, in this case, is your voltage, which is 12, divided by your resistance, which is 7.2. Let's do that. 12 divided by that. That gives me a current of 1.66, amps, pretty much. And so now we have the current that's running through that wire. We can easily find the voltage across light 1 because we know that... So if we know by Ohm's law, of course, so Ohm's law of the voltage is just resistance times current. We know now the resistance in the globe is 6, and the current that's running into it is 1.66 amps. So that's going to give us, times it by 6, that gives me 10 volts pretty much. So 10 volts runs through that globe, pretty much. Angela and Jenny now connect the secondary light 2, directly across the secondary of the transformer as shown. Here it's actually parallel. Now it's a parallel circuit, as you can see. So here now it's a parallel circuit. It's not anymore series, because if it was series, they would have added the light globe over here. But now they edited it like that. So I'm just going to draw a nice, like a circuit just for future questions. So again, you just draw pretty much your output voltage here. So, and of course you have a transformer. Now, we will have like a globe here, which is that, light 2. And of course we have our transmission line, and then we got our light 1. And it looks like that, pretty much. Overall, this is how our circuit looks like. And so, let's have a really, what's the question's going to ask us. Put it down here. They thought that with the circuit shown in figure 10, light 1 and light 2 would be equally bright. However, they observed that light 2 was brighter than light 1. Explain why light 2 was observed to be brighter than light 1. Easy. Let's really have a deep analysis of parallel circuits. So we know that, we're outputting 12 volts, yeah? 12 volts from our circuit, from our transformer. And if you don't know, in parallel circuits, this over here, this globe over here is going to have 12. Sorry, what am I doing? Ohms. Why did I do an ohms symbol here? It's 12 volts. In parallel circuits, the voltage goes for, so this here, this, this globe is going to get 12 volts of, pretty much is going to get 12 volts. And also this circuit over here gets also 12 volts. Because it's a parallel circuit, the voltage goes from both sides. It will be equal on both sides. So this here is going to receive 12 volts and this one's going to receive 12 volts. But the problem with this one over here is what? This 12 volt, it's not going to be given all to the globe light 1. It's actually going to also be given to the transmission lines. So the transmission line, let's say it takes, I don't know, let's say it takes 4 volts, the transmission lines. You're only going to be left out with 8 volts for this light globe. And so remember what we said. They sufficiently work, they said from the question, what did they say? That they worked at 12 volts. That the light works at 12 volts, if I'm not mistaken. Yeah. So both lights work at 12 volts. They efficiently work at 12 volts. So if this one, is actually receiving 12 volts, this one over here is receiving approximately like 8 volts or some figure we just made up. And so that's why it's light 1 in this case. So light 2, so light 2 is much brighter than light 1. And yeah, you can also, I think, explain it using power, which I'm not going to be honest. I think explaining it in terms of voltage is much more easier in terms of, this question. I think, yeah. So I hope that makes sense. Just remember, in parallel circuits, always remember, make sure you know some basic electronics. We know in parallel circuits, the voltage is going to be given. So if we're given 12 volts, the voltage is going to be given here 12 volts, and also it's going to be also given here 12 volts. But, this one, it's going to consume it by itself, that 12 volts, whereas this, it's going to split it with the, of course, transmission lines, and whatever its rest is going to give it to this globe, and it's not sufficient enough. And so that's why. I hope that really does explain and really helps you understand the concept that I'm trying to really apply here. So now let's write a statement. What's this 3 marks? So, what we said, the light globes are set in a parallel circuit. This is, by the way, all the things that I've talked about circuits, these are unit 1? Was it unit 1? Yeah, it's unit 1, physics unit 1 knowledge. So, yep, that. So globe 2, which was globe 2, or light 2. So globe 2 receives 12 volts, being directly parallel to the transformer, which is the required voltage for proper function. All right. So this explains why light 2 appears. So what am I doing? So light 2 appears brighter. I'm just writing. Oh my god, I'm writing so much errors in terms of spelling. So compared to light 1, so light 1 doesn't receive. So it doesn't receive the full 20 volts, the full 12 volts due to voltage loss in transmission lines. Hence, globe 1 receives less than 20 volts, so less than 12 volts, and appears less bright. And that is it. Pretty much, yeah. I think that here really kind of summarizes what I just talked about. Question 8. A car driver is driving up on a uniform slope with a trailer attached as shown in figure 11. The slope is angled at 15 degrees to the horizontal. The trailer has a mass of 200 kilograms and the car has a mass of 750 kilograms. Ignore all retarding frictional forces down the slope. Beautiful. So on figure 12 below, draw a labeled arrows to indicate the direction of the forces acting on the trailer. The label should also indicate the kind of forces that each arrow represents. So we have 3 marks, so probably 3 forces that we need to label here. I love these kind of questions, these fully forgot what they're called. I don't know. Fully forgot. Was it angle? Yeah, it was not bank angle, but yeah, fully for damn, really fully forgot what they're called. Yeah, quite a lot of exams have them. If you do like the NEEP exams and all those exams, they are always in, especially the TSSM exams. These questions over here are the most repeated questions. So that if you just practice and practice and practice, you will find these questions the most easiest. Especially this first question, that is just pretty much labeling the forces. So we know that there's going to be, of course, a force of gravity that acts towards, vertically downwards. So your force of gravity. And of course, we're going to have also a normal reaction force that'll be acting perpendicular. So N, we'll call it. Because it's through marks, we also need to include a tension force. Remember, there's going to be tension here, where it's going to go towards the car. So we also have a tension force overall. Yeah, these are, I think, the only 3 forces that you need to label. The car and the trailer are traveling at a constant speed. Look at the word constant speed. Constant speed tells us what? The acceleration is 0 and the F net equals 0. Always remember, when it's at constant speed up the slope, calculate the magnitude of the forces that the car exerts on the trailer. Show you're working out. So we want to calculate the magnitude of the force that the car exerts on the trailer. So is it this force over here that the car exerts on the trailer? But it doesn't matter, because remember Newton's third law, these forces are actually equal in magnitude. So it really doesn't matter which one it is. Both have the same magnitude. So it's just this tension force that we're trying to calculate. And so to do that, I'm going to break this down to its components. I know this angle here is 15 degrees. So it's overall, this here is going this way. So I'm going to take up the slope as positive. So it's going to be overall force of gravity sine, your F net. F net, I'm going to add these 2 forces because these are the ones that are accelerating it. So it's going to be tension minus force of gravity sine 15 degrees. Yep, to get this part here using basic trigonometry. And so because we know F net is 0, because acceleration is 0, like what we stated there, this here is just going to be 0. So your tension is just overall force of gravity sine 15 degrees, which is pretty much, force of gravity is just the mass times gravity. What's the mass of the trailer? It's only the trailer, the car trailer. Yeah, it's only the trailer we want. The mass of the trailer is 200 kilograms. So 200 times 9.8 sine 15 degrees. So let's do that. Sine 15 degrees. And so we get 507 newtons of force. Beautiful. Question C. Calculate the gravitational potential energy gained by the car and the trailer when they have traveled 100 meters along the slope. Show you're working out. So if it has traveled 100 meters up the slope, both the car and stuff, this is all we need to do. To calculate, it's one of the most ugliest, but yeah, overall, it will look like this. It's not a nice, but yeah, it does the job. So if the car has traveled 100 meters, let's say 100 meters here. And so we know this is, a angle, and of course this angle, what was it? 15 degrees. If we want to calculate the gravitational potential energy, which is GPE, which is mgh in this case, we need to calculate the height that he's traveled, which is this height over here. So we're just going to pretty much do basic trigonometry here. So to do that, we need to get the height. We know that this is your opposite. This is your hypotenuse. So we're going to be using, to get the hypotenuse, it's just going to be, so your height is just 100. So sine 15 degrees. Beautiful. So, and we can put this all into this formula. So the mass of both the car and the trailer, remember they're saying car and trailer, so you need to add both those masses. 200 and, what there? So 200 plus 750. So G is 9.8. The height is 100 sine 15 degrees. Beautiful. So 200 plus 750, 9.8, 100 sine 15 degrees. And that gives me, we want in kilojoules, so divided by 1,000. That gives me pretty much 2 for 1 kilojoules. Beautiful. That's it. Nice. Let's go to question 9. So 10 marks. Wow. I think this is the last question. So in a model of a proposed ride at a theme park, a 5 kilogram smooth block slides down a ramp from point W and into an ideal spring bumper without any friction or air resistance. That's good. So we're not losing any energy from that, as shown in figure 13. The final section of the ramp between point X and Y is horizontal. Okay, the block comes to an instantaneous stop at point Y. Okay, makes sense. Describe the acceleration of the block at point X, W, X, and Y. All right, let's really have a deep analysis of this. So let's have a look at when it's at W. What is the acceleration? So imagine, okay, it's, at rest. Imagine someone's holding it. The block has this resistivity. It just wants to go down at this, like, it's kind of in this angle. It just wants to go down. If you imagine you're holding it, it's at rest, but it has this acceleration that is acting downwards at an angle of this. It just has this, acceleration down the page. And so the block actually has an acceleration. And so this acceleration, because we know that overall that, G is going to be, of course, straightly down, straightly down. We can actually pretty much basically, actually, what we can do, I'm having a look at this. We can really do this. So this is going to go something like that. So that's the acceleration. So if I can break this kind of down like that, I can create myself a right angle triangle. And this is your G value, of course. And I can, let's say we can estimate this to be 15 degrees. I just want to understand, like, what, is it less than G value or is it greater than your G value in terms of when it goes? What's our acceleration? So, of course, this is your hypotenuse. And this here is your, this is your angle. This is your adjacent, so it's going to be overall G cos 15 degrees. I just made the angle, by the way, is equal to your acceleration. So we just made a value up, so 9 times cos 15 degrees, which is actually 9.5. So it's less than G. Your acceleration as it goes down the page, it's going to be less than G, of course. And of course, it's going to also be positive because it's accelerating. It's going to go down. It has to be positive. So what we can say is that at point W, the acceleration is less than G from, like, G is 9.8. And from what we've calculated as it's going to go down, it's going to be a value that's less than G, our gravitational strength. And it's also going to be positive because it means that it's, accelerating. And also the direction it acts down, we can say. Directly acts down. And yeah, just from basic calculation analysis, that's what I can pull out, from that whole calculation. So I'm going to rub this garbage out now. I was kind of too much, but because it's 4 marks, I really do want to be specific. So at point W, the acceleration is less than G and is positive and acts down. Done. Now let's have a look at X. So at X, all that energy would have been converted, of course, only to kinetic energy. So it wouldn't be moving at this position at like a constant speed. Now forget about it. Think about it. If it moves at a constant speed, what does that tell us? Acceleration is 0. Remember what we said from the last question? If let's say a block or something goes at a constant speed, its net force is 0 and also its acceleration is 0. So at X, it's just going to be, so at point X, the acceleration is 0. Because all the energy is all being converted to, kinetic energy. As it moves here, it's all going to be pretty much still kinetic energy. It doesn't change until we hit, our spring. So at point X, the acceleration is 0 as the block moves at a constant speed. Beautiful. And so the last one, at point W, at point Y. So as the block, pretty much hits this point and it, comes to a momentarily stop, it has this, urge to go to the left because, is being it got pushed, and so when it's stationary, it has this strong acceleration that wants to push it back to on the left, to go back and accelerate to the left. That's what's going to happen. So so at point, so we say we can say that, yep, so at point y, the acceleration is positive, of course, it's increasing. So yep, it's increasing, so of course it has to be positive, and acts left. That's all I can really find out, and acts left in this case, because we really can't really distinguish what else. Like, we can't calculate the acceleration, all that stuff. But I know for a fact when it's at this position and it's momentarily, it wants to really, it has this momentary acceleration that wants to just go to the left. And yeah, I think that would be enough to kind of explain what the accelerations are. Question B. The maximum compression of the spring is measured to be 3 meters, and its spring constant is that. Calculate the release height, H, show your working out. So 3 marks. So we're just going to use energy conservation. Just one of the most typical questions. So we know at point W, like they said, that it was at rest. And of course, the only energy that it has is your GPE, which is going to be at its max. And so when it's at Y, what do we know? We know GPE is 0 because it's not at a height, it doesn't have height, and it's momentarily at stop, so it doesn't even have velocity, so there's no kinetic energy. So all the energy when the block is here is the spring potential energy, which is SPE at its max. And we know both these here must equate, because remember, the total energy is always constant. So we can say mgh must equal to half k change in x squared. So so this is just overall, let me write it, k change x squared over 2, which is, so if I want to get rid of this mg, I'm just going to put them at the bottom then. 2mg here. 2mg. And that's it. That's our formula to calculate height. So height is just going to be k, which is 100 newtons. Your change in x is, of course, your how much, your compression was, which was 3 squared in this case, all divided by 2 times the mass of the block, which is 5 kilograms, times your g value, which is 9.8. So 100, 3 squared, 25, 9.8, and that gives me to, how many significant figures? We want to 9.2 meters. What a beautiful, nice questions. You get faster with these questions as you do more of these past VCAT questions. These questions are always repeated. I've seen this question, like, I think in the old exam. So yeah, you become quite quick, and your thought mind, when you look at any new questions, you can really, push them quickly. So this is the last page. Great. See, calculate the magnitude of the maximum momentum of the block, show working out. So we know that momentum is equal to mass times your velocity. So for the maximum momentum, it's the one that has the highest velocity. And we know that the highest velocity is where? It's at x, because remember, like what we said, of course, at this position, it is, momentarily at stop. Also at this position, it's momentarily at stop. So at x is where it would have the highest velocity. And so we need to also calculate that velocity in this case. To do that is, well, the most easiest case is to just take, use energy conservations again. So, for example, if I know that the total energy here is just all gravitational potential energy, here, the only source of energy here is just kinetic energy, because we don't have any springs, so no spring potential energy, we don't have any compression, and also it's at the ground, so there's no gravitational potential energy, so it's at its max. So we can equate these two pretty much. Or you can pretty much equate these two, but I'm just going to pretty much equate these two, just make my life easier. So I need to find, okay, I know that mgh is equal to half mv squared, so we can actually cancel those m's out, both have m's. So it's just going to be, we want to calculate velocity, so it's just going to be, so v is just the square root of 2gh pretty much, from, is that right? So 2, yep. So v is that. So 2, 9.8. What's the height? We did calculate the height, which was 9.2. I still have the exact value in my calculator, so that's good. And so putting this square root of 2, 9.8, that, I get a velocity of 13.9 13.416. All right. And so now momentum is just your mass, which was 5. Yep, so it was 5. Times that velocity, which is 13.416. And that gives me to how many sigma figures we want? To 267. Beautiful. And last question. When the block comes to rest, its momentum is 0. So in terms of principle of conservation of momentum, state what has happened to the momentum of the block as it comes to rest. Yes, what a nice question to end of the exam. It is quite hard to I think a lot of students will struggle with this question, but I think it was one of the old exams, this question was kind of similar. So this is what actually comes. So let's analyze what's going to happen. What has happened to all the momentum when it momentarily, comes to rest? So you know how it's going to go down, it's going to come back, oscillate until then, the block is going to come at rest, which will probably be around, this position here. Say it comes to rest. What has happened to momentum? Remember, conservation of momentum states that the momentum is always conserved. But where has it gone? Where has it transformed to? It's actually, think of it like this. As it, the block, hits both, like the spring, all that momentum is actually going towards the earth. Pretty much to the earth's surface. So imagine it oscillates. It just keeps, going into the spring, and the spring hits the surface, and it just goes towards down to the earth's surface. So all that momentum is all lost. It's not lost, but it's all transformed. It's all gone to the earth's surface. So I did remember this question. I remember doing it in one of those old exams, and yeah, it is a kind of hard one, but it's only 1 mark, so I wouldn't even worry about that. But yeah, just when if it's at 0, in terms of principle of conservation, state what's happened to the momentum of the block as it comes to rest, all that momentum has gone towards the earth or towards the earth's surface. So the momentum is transferred, yeah, not formed. It's not transferred to another energy, transferred to the earth's surface. And that is it. That is overall what our final exam is. I hope you guys enjoyed this video and learned something through this video. Please make sure to like and subscribe for more future videos. And thank you guys for watching. Have a great day. Bye-bye.